Hello, everyone. I want to talk about exponential distributions today. The meaning of exponential distribution, at least one of the meanings, is the waiting time of something happening. Or it can be also explained as the lifetime of something. Okay. For example, the lifetime of a bulb, a lifetime of a car. And in insurance industry, when we work with actuarial science, the lifetime of people also is assumed to be exponential. Okay. So it's the lifetime of something. The PDF is given by a constant times e to the negative lambda x, when x is greater than 0. Here, lambda is a parameter. Lambda is a parameter. X is greater than 0. So we try to figure out c, okay, using the fact that the integral from 0 to infinity, c times e to the negative lambda x dx, that equals 1. So do the integral, okay. The antiderivative of e to the negative lambda x will be 1 over lambda, actually negative 1 over lambda, times e to the negative lambda x. You can differentiate, sorry, I was thinking about differentiating it, so I put this prime there, but actually they're not equal to. What I'm saying is that you can differentiate this quantity and you would get e to the negative lambda x. Okay. X runs from 0 to infinity. When x is going to infinity, this quantity, I do need to assume lambda is to be greater than 0. Okay, that's assumed. Otherwise, this quantity will blow up. So lambda is greater than 0, so e to the negative lambda x, when x goes to infinity, goes to 0. That's 0. And minus, you have another minus here, it will be canceled out. So I will have positive c times 1 over lambda. And you plug in 0 for e to the negative lambda x, you get e to the 0, which is 1. So it's just c over lambda. And this is 1, so I know c equals lambda. So I have the density, which is lambda here. Lambda times e to the negative lambda x. Okay. The CDF is from integral, okay, integral from negative infinity to x f of t dt. Again, this is a definition, it's always true, but when you plug in lambda times e to the negative lambda x, then you need to change the lower limit from negative infinity to 0, and then the upper limit is still the same. I want to do a dt, okay, the t. Again, you have lambda. So antiderivative would be simply negative e to the negative lambda t. Okay, this lambda is there. And t is from 0 to x. You plug in x, you get negative e to the negative lambda x, and then you plug in 0, you get e to the negative lambda t becomes 1, so it's negative, minus negative 1, so it's 1 minus e to the negative lambda x. This negative comes from the minus, and this negative comes from this negative. Okay, so this is our CDF when x is greater than 0. A more important concept in exponential distribution is the survival probability. Remember I said earlier, exponential distribution could be a model to model lifetime of something. So the survival probability, what does that mean? It means the following. So suppose we have a random variable x, which say it's a lifetime of something. And then survival probability will be the probability of x greater than equal to some value, let's call it little x. Okay, so it means at time x, this something, this car or this bulb is still working, still surviving. So the probability of x greater than equal to little x would be integral from x to positive infinity. You have a lambda times e to the negative lambda t, antiderivative again, negative e to the negative lambda t, and you run from x to infinity for t, okay? You put infinity there, e to the negative lambda times t, when t goes to infinity, it's actually 0. So 0 minus, and you have minus, you plug in x, you e to the negative lambda x. So negative cancels out, you have e to the negative lambda x. So this is called survival probability. This one is simpler than that one. Again, the CDF has 1 minus in front of e to the negative lambda x. And the survival probability is just one term. So for exponential distribution, sometimes we use survival probability a lot because it's just easier to deal with. Okay, so let's have a look at an example, I guess. Oh, not yet. All right, let's find the mean and standard deviation. To find the mean and standard deviation of exponential distribution, an important integration technique is widely used. It's the integration by parts. Okay, I think I talked a little bit about it in another video. Integration parts, UDV. This is the version I like. Okay, that's equal to uv minus the integral of v du. Simply you switch the position. Okay, for these two. The one you see in calculus, another version. This is also it's a very commonly used version in calculus in Cal 1. So sometimes you probably see this u times v prime dx. You assume both uv are functions of x, and that equals u times v minus, then you have a u prime times v dx. But really, you put these things together, it's just a differential dv, and these two put together, it's just the du, okay? Remember, d of fx as differential is simply that. Or another way to think about it is the derivative is simply dfx over dx. At the beginning, when we introduced this concept of derivative, we sort of treating the fraction as one unit, one thing. Okay, don't separate them. But once we have the concept of differential, you can treat dx as one quantity and dfx as another quantity. So you can multiply both sides by dx, you would get this equation. Okay, anyway, it doesn't really matter which version you like when you deal with integration by parts. I personally like the first one, but you can do with the second version. All right, so let's find the mean. Say we have x, which has a density function, f of little x equals lambda e to the negative lambda x. Okay, where x greater than 0. And the parameter is lambda. Lambda is assumed to be positive. So e of x equals the integral from 0 to infinity x times lambda e to the negative lambda x dx. I'm going to put them together, so you'll get the negative, or actually d of negative e to the negative lambda x, you treat this quantity as the derivative of this quantity. Okay. Again, you can use whatever version, which version of integration by parts, that really doesn't matter. So this is the version I like. And then you just times put x and the negative e to the negative lambda x outside, but you do need to take care of the lower limit and upper limit. And then you have a plus, sorry, actually minus first, then it will become a plus later on. All right, so you just switch, make a switch. So you have negative e to the negative lambda x and dx. It's pretty easy because x dx, you don't need to work with other things. Just move x to the place behind the d, then you're done. Here, when x, well, this is a positive infinity, again, it's a positive infinity. When x goes to positive infinity, this goes to negative infinity, e to the z would be 0, even though x goes to infinity, but you can either use L'Hopital's rule to find the limit when x goes to infinity is 0, or you learn the fact that exponential functions go to infinity or go to 0 much, much faster than polynomials. So x is a linear function. Here you are going to infinity. Sorry, it actually goes to 0 because e to the positive lambda x goes to infinity pretty fast. So one over that will go to 0 much faster than x going to infinity. So eventually this term dominates, and if it goes to 0, it kills this x. So I have 0. And then you plug in 0, obviously plug in 0 to this x, you get 0, 0 times anything is 0. So this term will be just disappearing. And then we have a negative becomes positive. So you have 0 to infinity integral e to the negative lambda x dx. This, at least from the meaning of the probability, I know it's correct because e to the negative lambda x is positive, and you take an integral, it's also positive. So if accidentally you put a negative sign here or put a negative sign here, you have to realize that you're making a mistake because you will get a negative number in the end. All right, so this kind of little things you should keep in mind and keep track your calculations. All right, so the antiderivative of this, which is negative 1 over lambda times e to the negative lambda x. Okay, that's the antiderivative. X from 0 to infinity. If you plug in infinity to this term, it will go to 0, so you get 0. Minus becomes positive, 1 over lambda times e to the 0, which is 1, so it's just 1 over lambda. Okay, so we have the mean, which is 1 over lambda. Now we can talk about the meaning of this lambda. Lambda is the reciprocal of the mean time, mean lifetime of something. Okay, so and you look at this density function. You start from x equals 0, you get lambda. And when x goes to infinity, and you would have something like that. Okay, so going to 0. It should be sort of steeper normally. Something like this. Okay. All right. Now, when lambda is smaller, then you will have a flatter curve. So when lambda is smaller, so let's call it lambda prime. So lambda prime is smaller, so you have a flatter curve. And when lambda is bigger, then you will have a, say, let's call it lambda prime, double prime. Then it will be steeper. Hold on a second, let me think about it. Well, when they intersect, actually, I don't exactly know when they're gonna intersect. So let's just do some random thing. Okay. So this is when lambda the double prime is bigger, it's steeper. So it's steeper, that means the lifetime, the average lifetime is smaller. And flatter means the average lifetime is longer. So you have sort of a reciprocal relation. When lambda is bigger, then you have a shorter expected lifetime. Okay? So remember, that's the relation. By the way, some textbook actually uses a different version of this PDF. They probably would sometimes they use e to the negative x over u, and then you have 1 over u here. And this u is actually it's the lifetime, okay, average lifetime. Okay, but I think this is probably more commonly used. We're gonna use this version anyway. Uh, this is the mean. Okay, so let's talk about the standard deviation. But before we do that, let's find e of x squared from 0 to infinity. Lambda times, or x squared times lambda times e to the negative lambda x dx. Okay, I'm going to express the whole thing as differential. So d of negative e to the negative lambda x. Okay, and then we switch x squared. I mean, first of all, you don't switch. You need to have this term here, x from 0 to infinity, and then you have minus minus becomes positive. Okay, so you switch. The negative would be canceled out with the minus sign before it. So I have 0 to infinity, e to the negative lambda x, and then you have a dx squared, d of x squared equals 2x dx. Okay. This term, again, this goes to 0. When x goes to infinity, this goes to 0 faster than this quadratic term. So this will be 0 when x goes to infinity. And when x equals 0, obviously this term is 0. So eventually this will disappear. And I have this thing, 2x e to the negative lambda x dx. Okay. Now you can use integration by parts again, but I would suggest you not using that. It's the way of using the most recent tool, which is here actually. I'll tell you what I mean. I'm going to keep 2 there, and I'm going to put lambda here, e to the negative lambda x, and then I divide the whole thing by lambda. Okay. The reason I do that now, look at this term. Okay, this is something we actually know. So I move out 2 to the lambda, and x times lambda times e to the negative lambda x dx. Okay, this term is what? I want you to think about it. Well, in fact, it's the mean. So 1 over lambda. So I have 2 over lambda squared. That's our second moment. Then our variance equals second moment minus the first moment squared. So I have a 2 over lambda squared minus 1 over lambda squared because you are squaring it. So I get 1 over lambda squared. It's our variance. And finally, we have a standard deviation, which is 1 over lambda. So now you see that for exponential distributions, the mean and standard deviation are the same. Another distribution has a similar property but different property. Okay? It's the Poisson distribution. So for Poisson distribution, also the lambda, actually they are related in some sense. I'll talk about it later on. So Poisson lambda has mean lambda and variance lambda. So the mean equals the variance equals lambda. While for exponential distribution, um, the standard deviation and the mean are the same. Okay, so remember these properties. They can be used sometimes when you have a data. They can be used to check if data follow, say, Poisson or exponential distribution. Okay. All right. So these are the proper parameters. Let's work on an example, I think. Survival probability, we just did that. Okay. Suppose that the length of a phone call in minutes is an exponential random variable with parameter lambda equals 1 over 10. So lambda equals 1 over 10. If someone arrives immediately ahead of you at a public telephone booth, find the probability that you will have to wait more than 10 minutes, between 10 and 20. Okay. So I have a density equals lambda e to the negative lambda x. So I have that x greater than 0. So you arrive immediately ahead of you, so you can treat them like the same. Treat two people arriving at almost the same time, so infinitesimal time earlier than you. So we're gonna just treat like you are arriving at the same time. And it's a probability that you will have to wait more than 10 minutes. So the probability of x greater than 10. And then you have the survival probability. Okay, so it's from 10 to infinity. 1 over 10 times e to the negative x over 10 dx. But we actually have the survival probability we talked about earlier. It's just e to the negative lambda times this x, which is 10 here. E to the negative x over 10, and x runs from 10 to infinity. Put infinity, you get 0, so it will be, I think there's a negative sign here. So it's e to the negative 10 over 10, which is 1. Between 10 and 20, so I have x greater than 10, less than 20. You can use the integral directly, that's no problem. But I can also use survival probability, that is x greater than 10 minus the probability of x greater than equal to 20. But greater than equal to greater than, they have no difference in terms of probability. But now both are survival probabilities. I have e to the negative 10 over 10 minus e to the negative 20 over 10, okay? Remember the survival probability, which is 1 minus capital F of x equals, it should be e to the negative lambda x. Okay, that's the survival probability. All right, so it's e to the negative 1 minus e to the negative 2. Okay, so that's it. All right, next one. We have a very important property for exponential distribution. Oh, I'm going to talk about Poisson exponential property later. An important property is called the memoryless property. What means the following? But let's calculate this probability. Okay, so the probability that x will its lifetime will something will be surviving uh, to up to not up to beyond s plus t, given that x greater than s. So what it means this thing is that we know that something, say a bulb, a car, is still alive at time s. What is the probability that it will be still alive beyond time s plus t? Okay, so this is the condition probability we wanted to sort of calculate, and there will be some interesting result coming later. All right, review. The probability of A given B is the probability of A intersect with B divided by the probability of B. That's the definition of conditional probability. So we have x greater than s plus t. This is our event. Okay, intersect with x greater than s and divide by the probability of x greater than s. Now notice that x greater than s plus t, this event, is a subset of the event x greater than s. Okay, what it means is that if you know that something has lifetime greater than equal to s plus t, obviously it's you know that it's greater than s. You know somebody, you know the car survives at time 10 years. Obviously, you know the car works fine at time 5. Okay, so that's quite reasonable to think about. But we know if one set is a subset of the other, then the intersection will be just a smaller set, and the union is the bigger set. We don't care about that. We don't care about that, but we can use this equation. So essentially, the numerator of this fraction of this ratio is the probability of x greater than s plus t. Okay, and then the denominator is still x greater than s. We have greater than, so both are survival probabilities. So you have, again, let's repeat. This is our density. And the survival probability is 1 minus capital F of x. Capital F is the CDF. 1 minus that is the survival probability. Just e to the negative lambda x. Okay. So it's e to the negative s plus t, okay, with the parenthesis, and then the bottom is e to the negative s. That's e to the negative s minus t, but that's exactly the same as that. All right, we have the property for any exponential function e to the x times, so a to the x times a to the y is equal to a to the x plus y. And obviously you need to be able to work backwards as well. All right, so I have this fraction and you can solve that. That's e to the negative t. Okay. So what it really means is this. If you know something's still alive at s, the probability that it will be alive at s plus t is exactly the probability it will alive at time t, which means the fact that the something still alive at S is gone. The memory is gone. It's just like it's a newborn. It's still new, and it will survive at time t. Okay, so that's the meaning of a memoryless property. Okay, so you do need to be very careful though. It's s plus t, not t. So say, for example, simply say the probability of x greater than 12 given x greater than 3. Okay, it's not the probability of x greater than 12. It's equal to the probability of x greater than 9, which is 12 minus 3. Okay, well, we're talking about the exponential distribution. Okay, so you treat 12 as a 3 plus 9, and knowing that something is still alive at 3 and it will survive at 12 is basically you treat it like new and it will have 9 more years to survive. Okay, so it's exactly the same. Okay, this is called a memoryless property. You can check for uniform distribution, this property doesn't hold. Okay, and you do similar thing like you start uh, from this one. You can check it really quickly. Obviously, you will see why we can cancel out things because you are having exponential function. All right. So the relation between Poisson and exponential, they're closely related. Suppose you are sort of thinking about the Poisson process. By that I mean, so you have a timeline, okay? So you have a time where whatever the time goes on. So say, suppose you're police and you're sitting on the corner in the car, police car, and you try to catch some traffic violation. Okay, so the number of traffic violation is following, normally we can assume, okay, it's following a Poisson process. So you wait at time 0 and boom, 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 you got a traffic violation, and then wait again. Then maybe another time you will catch another traffic violation. So this whole thing, this process is called Poisson process. So you have those time of uh, traffic violations following uh, like on the chart. Okay, at this time you see you catch a traffic violation, and at this time you catch a traffic violation. Now, the waiting time is exactly exponentially distributed. Follows an exponential distribution with the same lambda. Okay, the Poisson has a lambda, right? So Poisson, it's the number. Poisson is the number of small probability events in a unit period of time. So let's see why these two lambdas are the same, and you can sort of making sense out of it. I'm not really proving they are the same, but you can sort of make sense out of it. For exponential lambda, we know the mean is 1 over lambda. Okay, and for Poisson, the mean is lambda. Okay, this mu is actually it's for Poisson. This mu is for waiting time for exponential. So don't argue. Well, why would 1 over lambda equals lambda? That's not the point. It's the mean for the Poisson is lambda. The mean for the exponential distribution is 1 over lambda. So if lambda is bigger, that means it's more often. It's likely to have a more often Poisson events happening. Then obviously the waiting time is shorter, right? More often. Then you don't need to wait more time. So that's why they have a sort of reciprocal relation. Okay? Or in order to prove actually that needs some work. But I try to make it reasonable that Poisson lambda, this lambda is 1 over the mean of the exponential. Okay. Yeah, I think that that's about it. Uh, This is the exponential distribution, and I think that's for today. I'll see you the next time. Bye bye.